Recording in progress.
So I'm just going to give a presentation about my Optimum interplanetary trajectory software from interplanetary to interstellar. And first of all, we're going to try and reproduce using OITS the Mars Insight Lander mission, which was a mission to Mars launched in 2018. And you type run_OITS at the command line, and you get this menu. And as you can see, there are various choices: open mission, new mission, save mission, etc., and a default mission name of test. Now we want to start a new mission. So obviously enough, we select new mission. Okay. And we get this drop-down box on the left here. And these are all the celestial bodies from which we can choose. And we have Earth barycentered there. You can see Mars barycentered there. We have further down at the bottom, we have Oumuamua, which we shall look into later. That's the interstellar object. And an intermediate point, which will have relevance again later on in the presentation. But for the moment, let's select Earth and then Mars barycenter, and they appear on the right-hand side there. And it's asking us to select a body number 3. We don't want a body number 3, so let's quit selection. Okay, quit selection. We are taken back to the main menu. I have now inserted the name, Mars_mission. And we now have to set optimizer details to constrain the search space. Let's do this. I shall now open my magnifying glass. And as you can see on the top line, we have Earth data. And on the second line, we have Mars data. And the earliest launch date is 2018, January the 1st from Earth. The latest launch date, 2019, January the 1st. So in other words, it's going to look for the optimal launch date within that year, 2018, which was the year that Mars Insight Lander actually launched. 10 there is, that's the minimum number of days it's going to take to get to Mars, and 500 is the maximum number of days it's going to take to Mars. At 200 kilometers, that is the circular orbit altitude that the spacecraft is going to start off with, orbiting Mars. We're going to check this box here. That's the rendezvous with destination, because once we arrive at Mars, we want to stay with Mars in its orbit around the sun. Okay. This 200 kilometers there at Mars is the point at which we apply that delta V. That's the distance above the surface of Mars at which we apply that thrust to stay with Mars in its orbit. Okay, so having specified all these parameters, the search space, as I say, we can now run the optimization. So I've clicked run optimization there. And these numbers here that's scrolling down are the delta V's. And what OITS is trying to do is minimize the delta V. Now, what is delta V, you ask? Well, it's essentially a measure of the fuel mass needed by the spacecraft to get from Earth to Mars. And by minimizing delta V, you minimize fuel mass. And by so doing, you maximize useful payload mass, such as a mass for the high-gain antenna, if you have one, or it may be solar cells, if you have those. But it may be, well, there will be instrumentation aboard, no doubt. So you can optimize that mass. So having performed this optimization process, let us now look at the results. So we select view results. And as you can see, we are presented with this table here. Okay. And we've got for the top row, we've got Earth barycenter, and the launch date is 2018, May the 11th. And we arrived 2018, December the 1st at Mars. That's the second line. And we have two pertinent parameters here, the delta V's. And the delta V at Earth is 3.57 kilometers per second. And the delta V to slow down at Mars is 828.7 meters per second. That gives an overall cumulative delta V of 4.4 kilometers per second there. Okay, so that's the lowest possible delta V. So let's see what this mission looks like. Let's do an animation of it. Let's see what it actually looks like by selecting animate results. We get the following. The inner circle there is Earth and the outer circle there is Mars. In fact, they're both ellipses, as you know, the orbits. The red dot is a spacecraft. And we launched from Earth 2018, May the 11th, that's down here. And we arrived 2018, December the 1st? Yes. Let's talk this again, just in case you missed it the first time. So we launched from Earth 2018, May the 11th. Takes a while to get to Mars. It reaches about 1.4 astronomical units away from the sun there. It's a speed, 23.4, 23.0 kilometers per second. So let's look at this and compare it with NASA Trajectory Browser. And NASA Trajectory Browser is an online tool where you can analyze trajectories to the planets that NASA has developed. Let's compare the results of OITS with the NASA Trajectory Browser. Seems a sensible thing to do. And we find the total delta V for the NASA Trajectory Browser is 4.36 kilometers per second, and compare that with OITS, which is 4.4 kilometers per second. So you can see that we're within 1% there. And for the delta V at Mars, we've got 821 meters per second post-injection delta V there. And we've got 828.7 meters per second for Mars. So we're fairly close. Let us now see whether we can reproduce a NASA mission that used a gravitational assist, because OIT is capable of modeling gravitational assists. Let's do this. So the New Horizons is just such a mission. It was from Earth to Pluto via Jupiter. Jupiter providing a gravitational assist, launched in 2006. And the duration of the mission, this is important, is constrained to 9.5 years. And you think what OITS does, it tries to minimize delta V. That means the mission duration could be quite long and extended. So we want to constrain that to make sure that we have reasonable mission durations. So now let's pointer working again. So these are the various parameters which we specify. New Horizons launched in 2006. So the earliest launch date is January the 1st, 2006. The latest launch date is 2007, January the 1st. The minimum flight time from Earth to Jupiter is 10 days, the max is 2,000 days. The minimum duration from Jupiter to Pluto is 100 days, and the maximum duration is 100,000 days. Now that seems to be rather long, but rest assured, down here to the left, I've specified a maximum duration of mission of 9.5 years. Okay, so it won't be any longer than that. These are the initial guesses I input there. And here we have 200 kilometers. That's a circular orbit altitude above Earth. We start off in. And 200 kilometers here is the minimum perigeo distance. So the perigeo is the closest approach to Jupiter. That means we don't want to get any closer to Jupiter than 200 kilometers. And in fact, what we find is that for this mission, the perigeo distance is much larger than that. So we have nothing to worry about, really, just to make sure. Check to rendezvous destination. Now with Mars, I checked that. With New Horizons, I haven't checked that. Because if you remember, with New Horizons, the spacecraft went beyond Mars and continued on its journey until it eventually reached an object we now call Atakoth, and took some photos of that and did some research there. So let's now run an optimization and compare the results of that optimization with Wikipedia, the real mission as achieved by New Horizons, which Wikipedia provides rather usefully. We have here to the lower right, we have the OITS results, and to the left, we have Wikipedia results, and those are the dates. So those are the pertinent dates from Earth It's 2006, January the 20th is the launch date. Jupiter 2007, March the 1st is when we encountered Jupiter. And 2015, July the 20th is when we finally arrive at Pluto. And we can see that those correspond fairly closely to the values we get. Let's go back. The values we get from Wikipedia. And if you look, the page-over distance turns out to be 2.3 million kilometers. And in fact, what New Horizons achieved was 2.3 million kilometer page-over distance. So we're bang on there. Let's go on. Excuse me. What I now want to do is see whether OITS can solve missions to interstellar objects. We know it worked for historical objects. Can we solve missions to interstellar objects, future missions? What is an interstellar object? Well, it's an interstellar object that originates from outside our solar system. The first one was discovered in 2017. It was called Oumuamua, which was discovered by Hawaiian Observatory, and Oumuamua is a Hawaiian name. It has this longitudinal, this cigar shape sort of morphology. I think it's more likely to be flat pancake shaped. So this is a meme which seems to have taken hold. In fact, it probably doesn't look like that at all. But it's what people picture when you say Oumuamua. Let's see what an interstellar object is exactly. It's first of all, an interstellar object is it's an interstellar object. It has a hyperbolic excess speed of 26.3 kilometers per second. So in other words, it arrived at the sun with a speed of 26.3 kilometers per second, and it will escape from the sun at the same speed in the direction of Pegasus. Its inclination, the inclination of the orbit, the orbital plane is tilted to the ecliptic by quite a considerable amount. It was discovered after perihelion, so that's the closest approach to the sun. So in other words, it was receding from the sun when it was discovered. And so it's a game of catch-up. In order to reach Oumuamua, we have to catch it up. So you have to go at a higher speed than it's traveling at, naturally enough. Makes sense, doesn't it? It has this unusual shape, and that was discovered by the light curve. It had a peculiar perturbing non-gravitational acceleration, and that is evidence of a force which was exerted on Oumuamua, and the exact nature of that force is unknown, but it's been speculated that it could be solar radiation pressure generated by a solar sail. So in fact, Oumuamua could be a huge solar sail, which is a means of propulsion which exploits the radiation of the sun and stars. This was suggested by Vilabers to say, so it could be of artificial origin, and the only way of finding out is actually to send a mission. So how do we solve a mission to Oumuamua? Well, we need a high speed to get there, as I say. Let's have a look at the trajectory that Oumuamua is on, and the orbit. You can see it zooming in from above the solar system, then is deflected back above the solar system by the sun's gravity. I think the inclination of the orbit is about 122 degrees, so it's a retrograde orbit, slightly. And you can see that it's going to a hell of a lick. So how do we catch up with this damn thing? Well, the KISS workshop, Science and Enabling Technologies for the Exploration of the Interstellar Medium. In 2015, the KISS, Keck Institute for Space Studies, performed an analysis into missions to the interstellar medium. And they discovered the way of getting to the interstellar medium, which is beyond 122 astronomical units. And they wanted to reach greater than 200 astronomical units in 20 to 30 years. So if you want to reach a high distance within a very short time, you want a high speed. Now this is precisely what we want with Oumuamua. So let's see what the KISS workshop came up with. Let's ignore the first two bullet points. To get to the interstellar medium, KISS decided that what we need to do is travel to Jupiter first, do a reverse gravitational assist to put on the brakes at Jupiter. So in other words, you slow down at Jupiter. You lose all your tangential speed. Yep. You then have only a radial speed towards the sun, and then you get very low perihelion. And a perihelion is the closest distance you get to the sun. So you get a very low perihelion value, at which you apply a thrust. This is known as Solar Oberth Manoeuvre, after the German scientist Hermann Oberth, who discovered it, I suppose. So it's a question of applying all your thrust at the perihelion point, and that maximizes your increase in energy, and that allows you to escape the sun's gravitational field with the maximum speed. You head off towards interstellar medium in the case of KISS. What we want to do, though, is head off towards Oumuamua. So we can use exactly the same strategy, but head off towards Oumuamua instead. So how do we apply this to Oumuamua? Well, I decided at the time that Oumuamua allowed you to select nodes that were celestial bodies, but you couldn't select a Solar Oberth Manoeuvre. So I needed something to model a Solar Oberth Manoeuvre. So I thought, well, let's try an intermediate point. I came up with a notion of intermediate points. What is an intermediate point? Let's have a look at this. An intermediate point is a point which is specified by the user. The distance from the center of the sun is specified by the user. That means it can sit anywhere on a sphere centered on the sun at that radial distance specified. And the exact point it sits is governed by two parameters. That's the heliocentric longitude and the heliocentric latitude. And these are the things that are optimized by my software. So my software, as well as optimizing the times of encounter of each of the celestial bodies in turn, it optimizes lambda and phi for that intermediate point specified by the user. So we can use this to generate or model Solar Oberth maneuvers. So here I am selecting the Earth first and Jupiter second, intermediate point, because that's when we want our Solar Oberth maneuver. And then we want Oumuamua between the Jupiter after the intermediate point, the Solar Oberth maneuver. And having done that, we can specify various search parameters. So let's do this. Take it from me, it launches in 2033. I did a lot of research into this. It definitely launches in 2033. That's the best time to launch. And there are various other data specified there, initial guess specified there. Go over to the right here, this 0.0279 at the astronomical units, that is, and that's corresponding to the intermediate point, and that's the radial distance we are specifying for the Solar Oberth maneuver from the center of the sun, and that corresponds to 6 solar radii. That turns out to be also the optimal distance for the Solar Oberth maneuver, and I discovered that also by conducting various research into it. And so let's run the optimization with this data. Okay. Oops. Wrong button. Okay, so what we find is when we run the optimization, we get a delta V of total cumulative delta V of 18.2 kilometers per second. That means that the mission is in fact achievable. So this is a mission that is quite viable and can be achieved in practice by a space launch system and 2 solid rocket booster stages at the Solar Oberth Manoeuvre. And that Solar Oberth Manoeuvre is requiring a 7.2 kilometer per second delta V. And the delta V at Earth, for launch at Earth, that's a hyperbolic set, in fact, of 10.952 kilometers per second. We can reduce that 10.952 kilometers per second by a small amount by introducing what we know as a V infinity leveraging maneuver before we get to Jupiter. So what we do is go from Earth, then do an intermediate point specified at 3.2 astronomical units away from the center of the sun. And then we return to Earth 3 years after launch. As you can see, 2030 June the 9th is when we launch, 2033 April the 17th is when we get back to Earth. And the point of the V infinity leveraging maneuver is so that we get to Jupiter with less delta V. Okay. And we find indeed this has reduced our total delta V down to 15.3 kilometers per second. And this means that we can get masses of something like 500 kilograms or so using a space launch system to Oumuamua. We have to subtract the heat shield from that because we're getting close to the sun as a result of the Solar Oberth Manoeuvre. So we need to subtract the heat shield. But that still is an appreciable mass. And let's look now at the animation of this trajectory. There it is again, the animation of the trajectory. Okay, we launch from Earth 2030, the red dot being the spacecraft, very obviously. And we get to 3.2 astronomical years. We then lose some delta V. And then we return to Earth after 3 years from launch. Having done so, we then head off towards Jupiter, exploit a gravitational assisted to Earth, then head off towards Jupiter. We then lose all our tangential velocity at Jupiter and head radially inwards towards the Sun in order to get to that low perihelion distance, at which point we can apply a Solar Oberth Manoeuvre. And you'll see the Solar Oberth Manoeuvre in a few seconds. At which point we hold the trajectory and zoom out so that we can see Oumuamua, which is heading away, you see. So it comes into the field of view. And we have, over the course of that mission, generated 15.3 kilometers per second delta V, you can see down here. However, the speed we have generated is 57.3 kilometers per second with respect to the Sun. And this enables us to catch Oumuamua after 22 years from launch. So I hope you've been entertained by this presentation. Thank you for watching. Just a few cursory details to finish off with. Let's have a look here. So we've got, first of all, Project Lyra. This is the logo for Project Lyra. This is the logo for Interstellar, Initiative for Interstellar Studies. And this is the organization that organized Project Lyra, which I was associated with. And then we've got Initiative for Interstellar Studies website here. If you're interested in the theory, a basic resume of the theory behind weights, then just look at Principium issue 27. That's the quarterly of the Initiative for Interstellar Studies. You have the GitHub repository for MATLAB there. That will give the theory document, which goes into detailed theory and equations that MATLAB OITS exploits to solve the interplanetary trajectories. Then you have Justin's web version without user interface. That's a web version which Justin, my friend, has constructed. And then my website finally at the end there. So there you go.